We tend to think of quantum mechanics as this perfect, ultra-precise theory that governs the tiny world of atoms. But it turns out our most fundamental theory has a secret, and believe it or not, it's a little bit chaotic. And that's a really important question, because once you move up from single, simple atoms to the complicated dance of molecules interacting with each other, well, that elegant math of quantum mechanics, it can actually start to fall apart. So what happens when our best theory just hits a brick wall? Well, get this. A groundbreaking new theory is saying that the fix isn't about adding more quantum mechanics. Instead, it's about embracing a brief, fleeting moment of good old classical chaos. And this isn't just some small tweak. Nope. It's a whole new way of looking at how molecules, medicine, and, yeah, maybe even life itself actually function. To really wrap our heads around this brilliant new idea, it's called quantum classical mechanics, by the way, we first have to understand the problem it's solving. Turns out, there's a subtle but really deep crack in the foundation of standard quantum theory. Okay, so for something simple, like a single atom, quantum mechanics is an absolute triumph. The predictions it makes are just stunningly accurate. But when you scale up to molecules, especially when they start bumping into each other and interacting, the standard theory can really struggle. The sheer complexity of all those electrons and nuclei moving around at once, it's a huge headache for physicists. And that failure? It actually has a name. It's called a singularity. This is a point where the equations just, well, they blow up. They start spitting out totally nonsensical, infinite answers when you try to calculate what's happening. And for physicists, that's a massive, massive puzzle. So how in the world do you fix a singularity? Well, you build a bridge. And in this case, it's a theoretical bridge that connects the predictable quantum world with the messy classical one. And that bridge is called quantum classical mechanics, or QCM for short. The core idea here is something called dozy chaos. Now, you gotta forget what you think you know about those clean, instantaneous quantum leaps. QCM says that when a molecule shifts from one stable quantum state to another, it actually passes through this blurry, chaotic, classical state for a split second. And that tiny moment of chaos, that's the secret ingredient that fixes the whole singularity problem. The whole process is actually pretty straightforward. A molecule starts off in a nice, stable quantum state. Then, for just a fleeting moment, this dozy chaos takes over and it behaves classically. And then finally, it settles back down into a new, stable quantum state. It's kind of like a quantum classical quantum sandwich. Okay, so that's the theory. But how does it actually work in the real world? Let's take a look at a classic problem that this new approach helps solve. What happens when two complex molecules smash into each other? So, picture this. You've got two complex molecules, and they're on a collision course. When they finally hit, they swap energy, and they start vibrating and spinning in totally new ways. This is exactly the kind of messy, real-world situation where the old theory would just throw up its hands and give up. I mean, the sheer number of moving parts in a collision like this is just overwhelming. If you tried to track every single piece, you'd get lost in the mathematical weeds immediately. So to make any sense of it, you have to simplify the problem, but without losing the important physics. And QCM's solution is just brilliant.
It makes this really clever distinction, dividing the molecule's parts into active and passive modes. You can think of it like a dance party, right? The active modes are the energetic dancers right in the middle of the floor, swapping moves really fast. The passive modes, well, they're the people kind of leaning against the wall. They're a bit too stiff or slow to jump into that initial chaotic energy swap. By just focusing on the active dancers, the whole problem suddenly becomes solvable.
So here's the thing. A theory, no matter how cool it sounds, is only as good as its predictions. Does this whole idea of dozy chaos and these active and passive parts, does it actually match what we see in the lab? This is the moment of truth, isn't it? A beautiful theory is one thing, but does it actually hold up when you compare it to real-world data? Let's find out. And this table right here, this is the payoff. QCM lets scientists predict a really specific value, they call it Na, which is basically just the number of those active dancing parts involved in a collision. And here's the amazing part. When they run the numbers and compare them to actual lab experiments, they line up perfectly. Just look at that last row. When these two complex molecules collide, the theory predicts about 19.3 of their parts will be active. And the experiments, they show the exact same thing. The theory works. So what's the bottom line? It works. This whole statistical approach, which was born from this idea of quantum classical chaos, it successfully predicts what happens in real molecular collisions. This isn't just some clever math trick, it's actually reflecting reality.
So we've solved a really deep problem in fundamental physics, which is awesome. But why should this matter to those of us who aren't in a lab? Well, because understanding how molecules trade energy is the absolute key to countless processes in biology and chemistry.
And the potential applications are just incredibly exciting. This new way of thinking could lead to huge breakthroughs in medical imaging, new cancer therapies, and even how we fight viral infections. The theory might also help us in the search for what some researchers call the molecule of life, some kind of structure that's complex enough to have that self-organizing spark that defines a living thing. And that brings us to this final, really provocative thought from the research itself. What if the fundamental spark of life isn't a molecule at all, but the very process this theory describes? What if, like the paper suggests, the true atom of life is the electron itself, and its transition through dozy chaos is the engine that drives all complexity? It suggests that a little bit of chaos isn't a bug in the system. It might just be the one feature that makes everything, including us, possible.